Welcome back to the deep dive. So today we're looking at a very specific piece of hardware, the NTI EACDCLM AC/DC voltage and current monitor. And our mission really is to get to the bottom of why this kind of simultaneous electrical monitoring is so absolutely critical.
Right. And we're essentially taking a technical product description and, distilling it. The goal is to figure out what this monitor can actually see in an electrical system.
And crucially, how accurately it sees it.
Exactly.
Okay, so let's start with the basics. The device is handling 4 critical measurements, right?
That's it. AC and DC voltage and AC and DC current.
It sounds like the perfect multi-tool for anyone managing, power infrastructure.
Well, what's fascinating here is the prerequisite. While the voltage part is handled internally, the current measurements, they rely completely on external Hall effect transducers.
Ah, okay. The kind of specialized sensors you need to add on.
Precisely, and they're sold separately. So you have to think of this monitor as more of a brain or a data funnel that reports everything back to a larger host unit.
The E2D, 5D, or 16D models, I see.
Yep, those are the ones.
All right, let's get into the specifics on the voltage numbers because I feel like this is where the precision really counts.
It absolutely does.
For AC voltage, the range is 0 to 240 VAC, and it includes 600 V isolation, which that's a serious safety feature.
Oh, it's critical, especially when you're near high-power switchgear. And you have to pay close attention to the accuracy here because it's variable.
Am I constant?
No. For the lower end, so 0 up to 220 VAC, the accuracy is pretty tight at 2.5 VAC.
Okay.
But as you push into that higher band, from 220 up to 240 VAC, that accuracy widens to 5.0 VAC.
So there's a bigger margin for error right at the system's limit.
Exactly. It's a classic sign of behavior under maximum load. It means you have to factor in a potential 5-volt swing when you're running near that 240 V limit.
And now on the DC side, it's working in a range of -60 to +60 VVC with a 1.2 VDC accuracy. But you mentioned the AC side has that 600 V isolation. The DC side is non-isolated. What's the engineering trade-off for that?
It usually simplifies the design. And it can lower the cost for systems where the DC voltage is already, within safe low voltage limits.
Like telecom power or big battery backup?
That's the perfect example. You gain simplicity because the risk profile is just lower than being right next to high voltage AC mains.
So for the current measurements, if the transducer is doing all the heavy lifting, what is the E-ACDCLM itself actually contributing?
It's providing the vital interfaces. It has one rectifying interface for AC current, so it converts that signal, and one non-rectifying interface for DC current.
And the resolution is high on both.
Very high, 0.2% resolution, which ensures the data stream back to the main ENVIROMUX unit is precise. And it's fast, polling at 1 sample per second.
Okay, so connecting this to the bigger picture, where do we actually find a device like this working? I mean, this box is tiny, only about 6 by 2 inches.
You find it anywhere. Power reliability is paramount. So we're talking data centers, substations, backup generators, even medical equipment.
And it gets its power directly from the host unit.
Yep, directly from the E2D, 5D, or 16D. No separate power cord needed, which is a big plus. And the connectivity is really flexible. You can run a standard CT5 cable up to 1,000 feet.
1,000 feet? For a large facility, that's substantial.
Oh, yeah. Any IT manager would be happy with that.
But this is where it gets really interesting for me. What if you need to monitor something miles away?
And that's where the flexibility really shines. You can integrate fiber converter extenders that will push the signal up to 1.2 miles, so about 2 kilometers, from the main ENVIROMUX unit.
2 kilometers.
Yeah.
That fundamentally changes where you can place your monitoring sensors.
It really does. So I guess the final takeaway is this. This device simplifies some really complex electrical monitoring into a compact, connected, and TA-compliant form factor.
Trade Agreements Act compliant. That's essential for government bids.
A huge deal. And it's capable of stretching its sensors across some really vast distances.
Which brings us to our final thought for you to chew on. Considering this monitor's use in substations, data centers, and medical equipment, how does that very specific shift in accuracy, that difference between 2.5 AAC and 5.0 VAC, how does that directly impact the reliability and safety of the critical infrastructure we all rely on every single day? Something to think about until our next deep dive.